Welcome to this video on solving systems of equations by Gaussian elimination. Gauss was a mathematician who's credited with the solving technique that you're going to see in this video. We're going to start with a discovery that was made centuries ago. It was discovered that if you have a system of linear equations, and you were to create a new equation out of it by taking a multiple of one equation and adding that multiple to one of the other equations, and you were to then replace one of the original used equations with the result, that the new system of equations would have the same solution or solutions as the original one. To give a little bit of a sense of what this means, let's look at an example. Here is a system of equations. Suppose I were to multiply the first equation by -2 and add it to the second. By the way, I just made up -2 sort of randomly to show as an example, because the discovery says that this works for any multiple of any equation. So if I were to take the first equation, say, multiply it by some random number, say -2, and then add that to the second equation, here's the sum of those two equations, you'll notice. The discovery states that if I were to take that sum and put it in place of either equation 1 or 2, then I would have the same system in terms of solutions. So if I were to put that here, then this system of equations would have the same solution as the original. Or if I were to put that sum here, then this system of equations would also have the same solution as the original. This would not work if I replaced the third equation with the sum, because the third equation wasn't used in creating it. Now, in order to fully understand this video, a decent understanding of what this discovery states is crucial. So before we even get to the part of the video where we're using this discovery in a productive way, I have a section here where I'm going to have you, as the viewer, practice applying this discovery. So, what I'd like you to do, get yourself some scratch paper and get ready to hit pause several times and work through this little mini worksheet, because it will give you a more concrete understanding of what this discovery actually says. So get ready to hit pause and get ready to start working on some paper. Here goes. First, I'd like you to take any random multiple of any of the equations chosen. Hit pause. Okay, now you should have picked any of the three equations and multiplied it by any number you wanted. Let's proceed. Now choose another equation. Literally just pick one of the two equations you didn't use in the first step. Hit pause. Okay, now add those two equations together. Hit pause one more time. Okay, now what you're going to do is you're going to replace either of the original equations that you've used so far with the result of the sum, and rewrite the entire system here in this box on the left. You may see it as blue. So just to be clear, you're going to keep two of your original equations and replace one that you've already used. So maybe you'll keep the last two and replace the first one if you use the first one. Maybe you'll keep the first and the last and replace the second if you use the second one at all. Or maybe you'll keep the first two equations and replace the third with the sum if you did in fact use the third to create that sum. Hit pause now and rewrite your new system of equations. Okay, now I would like you to solve both systems of equations here, the original system and the new one that you've created, 2/3 of which is the same as the original, as if they were separate math problems. To do this, you can use any technique you've used in the past. Most likely you've used substitution or the addition-elimination method, which is different from Gaussian elimination that we're learning here, but you may have also learned about Cramer's rule or matrices using inverses. Who knows, but whatever techniques you have from your toolkit in the past, solve both of these as if they were separate, unrelated math problems. Hit pause and solve both systems. Now that you've solved both systems, if you did your algebra right, you should have discovered that in each case, the solution to the system was x equals 1, y equals 2, and z equals 3. And what this does, remember, we are not at the point in this video yet where I'm teaching you how to use Gaussian elimination. What this worksheet that you've done does should convince you that the discovery works. In other words, you've taken a random multiple of an equation, added it to another equation, then replaced one of those two equations with a sum to create a new system, and you should have seen for yourself that solving both of these systems leads to the same solution. This discovery is fundamental to the understanding of Gaussian elimination, and if it didn't work for you, rewind all the way back and start over. Do not proceed until you have a decent understanding of what this discovery says. And if you do, let's continue. So we're going to take a look at how this discovery evolved over time to create this technique credited to Gauss called Gaussian elimination. Here's a system of equations. And I want to warn you that this portion of the video that you're about to see has a lot of detail in it because it shows the sort of the beginning of how this whole technique came about. And the first, as you see this first example, you're going to see the beginnings of how it started historically, and I just want to reassure you that we will later in the video get to it in its more modern incarnation, and that's sort of the more how-to moment in this video. But right now we're still in the exploring stage. So what you're about to witness on this system of equations is not what you would actually do as a student in the 21st century. Here goes the beginnings of the historical evolution of this topic. So what a mathematician would have done centuries ago is multiply some equation by some number and add it to another equation. In fact, we saw this very one in the beginning of the video. This is the end result of me applying this. And what mathematicians were going for here was the elimination of variables. Look at the second equation in each of these. In the top, the second equation has an x, y, and a z. In the bottom system, the second equation no longer has an x. The thought was, if we could choose clever multipliers and add clever equations together, that we could eliminate variables in one fashion or another. And the more variables we eliminated would lead us to a more likely solution. or the likelihood of finding a solution. If right now you're feeling like, I don't understand where the -2 came from, don't worry, we're not in the how-to portion of this video yet. I'm simply showing you what mathematicians have done in the past. And they've noted that if they multiply certain equations by certain clever choices of numbers and add them to other equations, that they can eliminate variables, and that's what happened here. So suppose a mathematician then were to choose this. It turns out that that would eliminate yet another variable. If you're feeling confused, hit pause and actually perform these operations yourself as if you were the mathematician from centuries ago. So now we've eliminated more variables, and the thought was the more we do this, the closer we'll get to a solution for solving for x, y, and z. So the next thing that a mathematician might have done is multiply the middle equation by -4. This is not technically the same as the discovery, but it was also discovered that if you multiply an equation by any number, that it doesn't change the solutions to that equation. You've known this since middle school. And so there I've multiplied the equation by -4, and it may seem weird, that it may seem like a random choice. It did not eliminate a variable. It turned this number into a 12. Now, I'm actually the mathematician who did this, but I deliberately chose to multiply by -4 to make that a 12. Why on earth would we want to have a 12 there? Watch and you'll see. If I then multiply the third equation by -1 and add it to the second, I'm effectively using the 11 to turn the 12 into a 1. And then I could then multiply the second equation by -11, thus using that newly created 1 when adding to the third equation to cancel out a y. And this is the result of all of that work. Again, most students watch math videos with the intent of being shown how they can do something. That is not what's happening here. What's happening here is I'm showing you what mathematicians have done to give you a broader sense of what this topic is. Look at the third equation in the very bottom. Because of some very clever choices of applying our discovery, I have gotten the bottom equation down to a single variable. The numbers are not something you should focus on specifically, but the concept that I've gotten the x and the y out of that bottom equation is really the key here. Because now, if I were to just multiply the bottom equation by this fraction, you could think of it as dividing by -328 as well. By applying this other discovery that we can multiply any equation by any number, then all of a sudden I have this equation, this system of equations, in a very solvable format. Let's take a closer look at what we've done here. We've taken the system of equations on the left, and we've made some wise choices about how to apply our centuries-old discovery. And what the discovery says is that the system of equations on the left, the one we started with, will have the same solution as the system of equations on the right. So the key idea here is that if you choose wisely about what to multiply and what to add, you'll get your system of equations into a much more solvable form. Would you rather solve the system on the left, or would you rather solve the system on the right? I would choose the one on the right. Most notably, the third equation on the right tells me what z is. I have effectively solved for one variable already. In fact, if you look at the structure of these equations, ignoring the numbers, The top equation has 3 variables, the next one has 2, and the next one has 1. And Gauss figured out that this is an ideal kind of system of equations to have to deal with, because if we know that z is 4, we can plug that into the second equation and find out what y is, which we'll do in a moment. But then imagine knowing that what y is also, and knowing z is 4, I could then plug those 2 pieces of information into the first equation and solve for x. I'll show you that algebra right now. Plugging 4 into the top 2 equations and simplifying allows me to solve the second equation for y, and then plugging y equals -3 into the top equation and simplifying allows me to solve for x, and I'm now done with this problem. Now, you might be thinking, I already know how to solve systems of equations. Why would I want another technique created by Gauss, or credited to him anyways? That is just a tough question to answer, except to say that the more techniques that you learn, the smarter you get. And also, this technique has an element of seeming randomness to it. You have to pick random equations and multiply them by seemingly random numbers and eliminate variables. But the truth is that it's not random if it's productive. And the act of choosing productive things to do to turn a complicated system into a simpler one is something that's good for your brain and just good for general thinking skills. So with that philosophy in mind, let's continue. So what just happened? Well, we used this discovery repeatedly until we got the result we wanted. But there are 2 things that aren't optimal at this point, I guess we could say. One, that this technique involves some pretty messy algebra, as you witnessed. And it requires a creativity of a kind where you're not really following a specific procedure. You have a goal of eliminating variables, but there's no clear guidance on first do this and then do this. So in this video, I'm going to attempt to give you a way to deal around both of these problems. I'm going to start this video by showing you historically how mathematicians have cut down on the messy algebra. Here's the same system of equations that we've already solved. And you'll recall that the first thing we did is multiply the first equation by -2 and add it to the second. We saw several times in this video that this is the result when replacing this original second equation with that sum. This we've already seen. But mathematicians, centuries ago, after this discovery was made, had an idea. Some mathematicians, and I honestly don't know who or if anyone ever got proper credit for this, but it was thought of that we could simplify this process by not writing any of the letters, which typically were X, Y, and Z, but technically could be any letters. And if you look at these 2 columns of information, they look different, but they have the same numbers. I recommend hitting pause and convincing yourself that the left column and the right column contain the same information. So instead of saying we're going to multiply the first equation by -2 and add it to the second, over the years, this notation that you see on the right, you may see it in purple, this has developed. And what it describes is the exact thing that you've already seen. It's an application of our original discovery. So if we were to take this row and multiply by -2, and add it to this row, this would be the result. I want you to convince yourself of that. Hit pause now. You should have convinced yourself that this is exactly what we've been doing all along in this video. So the idea for mathematicians was this. Let's just eliminate all the need for writing x's and y's and z's over and over and over again, and instead just keep the numbers in rows and columns that represent x, y, and z. You'll see the dotted line in this matrix of numbers that represents where the equal signs were in the equation. And the numbers on the right of each matrix, which you may see in green, representing the numbers after the equal signs or the constant terms. So what if we were to take this and do the same process of elimination of variables without actually seeing the variables themselves? Now, I'm going to guide you through this as a mathematician would have done. And at the end of each step, you're going to hit pause and do the mathematics yourself. If you're not able to follow the mathematics that you're going to see here, you're going to have to keep rewinding until you get it. All right, it's time for you to work on scratch paper. Here goes. I'd like you to take the second matrix and perform this operation. In other words, multiply the first equation, which we're calling row 1 instead of equation 1. Multiply row 1 by 3 and add it to the third row. Hit pause and do that now. This should have been your result. Now take that matrix and multiply the second row by -4. Hit pause now. This should have been your result. Now take that matrix and perform this operation. Hit pause. Okay, this should have been your result. Now take that matrix and perform this operation. Go ahead and hit pause. This should have been your result. And finally, perform this operation. Pause now. This should have been your result. So what you have just worked your way through with my guidance is the exact problem we already solved earlier in this video. But what you've done is you've done it in the tradition of Gaussian elimination, where you're writing the coefficients of x, y, and z without writing the letters themselves. And what Gauss and other mathematicians discovered is that if you could convert your solution into a matrix like the one on the right, that you would be in a good position to solve. Notice there's something very special about the numbers that we've gotten on the matrix on the right side of the screen. We have a diagonal of 1s from the upper corner in a downward right fashion. That's called the main diagonal of that 3 by 3 matrix to the left of the dotted line, but that is not the focus of this video. The point is we've got this diagonal row of 1s with 0s underneath it. Once we've converted our system of equations into a matrix of this type, we call that row echelon form. There's a long history behind that name, and it isn't the point of this video to go that deep into matrices, but that is the name of this format. 1s on the diagonal and 0s underneath that diagonal. And the reason why Gauss and others figured this was such a valuable thing is because then we can convert it back into a system of equations by actually reinserting the x's, the y's, and the z's, and the equal signs. And the nice thing about having those zeros where we have them in particular, and also having the ones where we have them, is because this system is the same as this system. Notice these two are the same. These two are the same. And these two are the same. So to restate what we've already seen, by converting our system of equations to a matrix in row echelon form, we have now discovered what z is. We can use that value of z to find y in the second equation, and once we find y, we could then use the value of y and z in the first equation to solve this system. And we've already actually seen that algebra earlier in this video. So what you've seen here is a way of dealing with the algebra and making it less messy by not writing the variables over and over again. And what I want to attempt to help you do now is to deal with the notion that it still feels a little random that you're just taking any old equation and multiplying by any old number and hoping to magically cancel out variables in other equations. And that can feel a little unsettling as a student. I'm going to do my best to take the creativity element out of this. You can't remove it completely, and now maybe I wouldn't want to, but I'm going to show you now what mathematicians have traditionally done over the years in a way to sort of proceduralize this to the degree that it's possible. So here is the same system of equations that we've been working with this whole time. And to use the Gaussian discovery, we want to convert this into row echelon form, meaning we want ones on the main diagonal and zeros all underneath those ones. That is the goal that we're looking for. You've already seen this happen. You've already performed a lot of the algebra yourself. We're going to take another look at it now in order to more codify and procedure how to go about this in a more step-by-step and less random seeming fashion. So to convert something into row echelon form, the first thing you want to do is convert the original matrix or the original system of equations into a matrix. In other words, just write down all the numbers in the equation, put a dotted line where the equal sign is, and proceed. The first thing I try to do, and most mathematicians try to do, is they try to get a 1 first in the upper left corner. Remember, we need a lot of ones and a lot of zeros, but we generally tend to start with that. In this particular problem, we already have a 1 there, so that's a good start. Next, what I and most mathematicians do is try to achieve a 0 underneath that 1. So what I would do then is try to use the 1 to cancel the 2. And to do this, we have to use the original discovery from the very beginning of this video. So the best way to use the 1 to get rid of the 2 is to multiply the top row by -2 and add that to the second row. If you'd like to hit pause and perform this, you can, but I should point out you already performed this a few minutes ago. And this is the result that you got. So now that I have a 0 underneath that 1, the next thing I typically go for is to get a 0 underneath that 0. And I like to use the 1 to create that bottom 0. what I can do is use the 1 to cancel out the -3. The way you did this earlier in the video was to multiply the top equation by 3 and add it to the bottom equation, or technically the row, not equation, but really they're one and the same. So this is the result you got earlier when you performed this math. So if you look in the upper right corner of the screen, the 1, 0, 0, we've sort of created the first column the way that we want it. And we're now getting closer to row echelon form. The next thing I like to do is move to the second column and create a 1 there where I need it. Now, currently, we have a -3 in that slot. So I thought of this pretty clever thing, if I do say so myself, of multiplying the second row by -4, because what it did is it changed this -3 into a +12. And again, you have to ask yourself, why on earth would we want a 12 there? Well, ultimately for row echelon form, we don't want a 12 there, but my thought was I could then use the 11 to turn the 12 into a 1 by doing this operation. Because multiplying the third row by -1 makes that a -11, and then adding that result to the second row turns the 12 into a 1. You did this earlier in the video. And now I have the 1 where I want it. And now I'm going to use that 1 to get a 0 underneath it. In other words, I'm going to use the 1 to cancel the 11. And as you did earlier, you multiply the second row by -11 and add it to the third row. This is the result you got earlier. And finally, to get into row echelon form, I need a 1 here, but that just essentially involves dividing the third row by -328, or multiplying by the reciprocal of that, same thing. And now I've given you a more roadmap to follow, I guess we could say, on how to get, in what order to get the numbers you need in row echelon form. To summarize this slide, I like to go column by column. If you look at the upper right corner, as I say this, I like to work my way through the first column first, meaning get a 1 and then use that 1 to get 2 zeros underneath it. Then go to the second column, get a 1 in the middle, and use that 1 to create a 0 underneath that. And then go to the third column and get a 1 there, essentially by division, if you want to call it that. And now you can see that we've converted this to row echelon form. And as we saw earlier, once you do that, you're in a better position to solve the system of equations. So again, start by getting a 1 here, use that 1 to get a 0 here, and to get a 0 here. Then somehow get there to be a 1 here, and then use that 1 to make this number 0. And finally, multiply by the reciprocal to get this number to be 0. I want to add one more thing to your Gaussian elimination toolkit called switching rows. Imagine we're solving this system of equations. We write it out as a matrix. And remember, to get to row echelon form, we want a 1 in the first slot. But we have a 2 there now. However, we do have a 1 here. So if I were just to interchange row 1 and 2, I would have a 1 in this desired slot. And it shouldn't come to a surprise to anyone that switching rows is a valid mathematical option at any time you so choose. Because switching rows is really just a reordering of the equations. And of course, if we reorder the equations in a system, we're not changing the solution. So at any moment that it's advantageous to you, you can interchange any 2 rows in the matrix without altering the solution, and thereby still getting the same solution to the system of equations. Let's now add another idea called reduced row echelon form that will make it even easier to solve systems by Gaussian elimination. Here's the same system of equations we've seen several times in this video. And as we saw earlier, by converting it to a matrix and then using the row operations to get that matrix into row echelon form, we were then able to turn it back into a system of equations that was simpler and easily solve that system. Mathematicians had an idea centuries ago, and they wondered, what if we were to take the 2, the 4, and the 31 in this problem and continue to use row operations to make those also become zeros? Watch the end result of this very clever idea, and get your scratch paper ready and get ready to hit pause. You'll be doing some of the work yourself. First, perform this row operation on the matrix. Hit pause and do that now. This should have been your result. And notice we got a 0 above the diagonal of 1s. Now perform this operation. Hit pause and do that. You should have gotten this result, thus creating another 0. And essentially what we've done is we've created 2 zeros above the 1 in the lower right corner. Now, there's one number left that isn't on the diagonal, that isn't 0. And to get rid of that 2, perform this matrix operation now. Hit pause. You should have gotten this result. So the question then becomes, why would we want to go past row echelon form into reduced row echelon form, which, by the way, means 1's on the main diagonal and 0's both above and below all of those 1's? Well, because if we are willing to take the time to go from row echelon form to reduced row echelon form, we will then have a system of equations that's very, very simple to solve. In fact, if you're willing to hit pause and analyze it, you'll quickly see that that system of equation with all those 0's and 1's in the strategic places is equivalent to this system. In other words, reduced row echelon form, as opposed to just row echelon form, the reduced row echelon form literally gives us the answers for x, y, and z. So if you're willing to perform enough matrix row operations to get to reduced row echelon form, you then have the system's solution staring you right in the face. Kind of handy. There are some situations that are a little unusual, but they do arise from time to time when using Gaussian elimination, and I want to warn you about those now. Here's a different system of equations. This is not the one we've been working with for the last probably over an hour of your time. So brand new system. Suppose we were to convert this into a matrix and then try to reduce that matrix to row echelon form, getting all the strategic 1's and 0's in the right places. Now, this video does not show the work, but you will eventually, after lots and lots and lots of work, end up with something like this. This may not be exactly what you would end up with, but what you would end up with one way or the other is a row of all 0's. And it turns out that you cannot get this matrix into row echelon form, much less reduced row echelon form. It's literally impossible to do so, mathematicians have proved. But what does this row of all zeros mean? It means this. And there are so many different solutions to this equation, it's essentially a non-statement. And what a row of zeros really means when you think about it is it adds no information to the problem. And in effect, what we have here, even though the original system appears to have 3 equations in it, and it literally does, it only contains as much information as 2 equations would contain. Now, linear algebra is a very deep and rich subject, and we won't attempt to get into it in this video. But the sort of the shortcut end result of what you need to know is that if you get a row of all zeros, it is an indication, first of all, that you'll never get to row echelon form, and you'll never get to a single solution to this equation, because when this happens, your system of equations has infinitely many solutions. And that is essentially the end of where we can go in this problem. Now, some courses will have you find all infinitely many solutions. Other courses will have you simply state that there are infinitely many solutions. But either way, when this happens, that's an indication of that's the kind of system you have. Your teacher may have called it a dependent system of equations, depending on what you're studying at the moment, or they may not have called it that. Here's a similar problem. Well, not similar in appearance, but similar in end result to some extent. Suppose we were trying to solve this using Gaussian elimination, and we converted to a matrix as we always would. And then we went through all the row operations, all the getting the ones and zeros in the right place to try to get to row echelon form. It turns out, in this case, after lots and lots and lots of work, you can't get there either, because a similar thing happened. Should you ever, in the process of going to row echelon form, get a row of all zeros except for the constant number in the corner, the 3, this is an indication that this statement would have to be true for there to be a solution to this problem. But wouldn't you agree that it's impossible for that statement to be true? 0 times a number plus 0 times a number plus 0 times another number can't equal 3. That's not possible. So whenever you get a row that has all zeros to the left of the equation and a non-zero number to the right of the equal sign, that is an indication that that equation has no solution, and therefore the original system has no solution whatsoever. So keep an eye out for these 2 situations, as they do happen from time to time, as rare as they are. You have to sort of be aware of them. So in summary, a discovery was made centuries ago that enabled mathematicians to solve systems of equations in a more efficient manner. We saw this system of equations as an example, and when you're given a system of equations, convert it to a matrix. Use any row operations of your choice. That's your job, to create either row echelon form or reduced row echelon form, either one, thus leading you to a system of equations that's much simpler to solve than the original, either one of which will lead you to the solution in the end. I hope this video has helped you get a better understanding of what Gaussian elimination is, and that concludes this lesson.